Welcome to the UGC lecture series. This is the EPG Pathashala lecture series and the subject we are talking about is computer science and the paper we are talking about is data structures. Now, in this particular module we are going to discuss a very important and interesting data structures, the trees. So, we are going to talk about trees as a abstract data type. So, these are the people responsible for the creation of this module. And now, let us look at the learning objectives of these this particular module. We are going to explain the concept of trees, what are trees and what are they used to represent. We are going to discuss general trees with some examples. Normally, in your previous introduction to trees, you would have discussed more on binary trees, we will discuss that later, but here we are going to talk about general trees in with some examples. Then we are going to discuss the representation of general trees, and finally, we are going to explain the different tree traversals. Traversal is a very important operation as long as tree is concerned, and we are going to discuss how to convert general trees to binary trees, because most of the algorithms and most of the applications try to talk about binary trees, but unfortunately it is not possible to represent everything as binary trees. So, it is necessary to study a little bit about general trees and then talk about how to convert these general trees automatically to binary trees. So, we will be looking at that also, and the keywords of this module are trees, general trees and traversals. So, let us look at trees. What are trees? We have discussed up to now only linear data structures. Okay. What are the data structures we have discussed? Arrays, linked list. Okay, linked list and arrays were used for many things, but lists basically, stacks and queues. Stacks and queues were restricted lists. Okay. So, stacks was a first in first out policy, while queues followed the last in first out policy. Sorry, stacks followed the last in first out policy and queues followed the first in first out policy. That was what we discussed, that is restricted insertion and deletion was what we were talking about, and we talked about a lot of interesting applications of these linear list data structures, but all other data structures cannot be linear. We also talked about there are other data structures that we will consider, trees, tables, graphs and hash tables. Some hash tables we have already seen. So, we will be talking about these also as we go along. Trees are very useful and suitable for a wide range of applications. So, all applications you cannot do using linear lists. So, sorting, searching, expression evaluation, data set representation, they are all recursive algorithms and they can be all used, trees are better representation for those type of applications. Now, let us look at some terminology here. A tree consists of a finite set of elements, there should be a finite set, and these set of elements are represented as nodes or vertices. Normally, in trees they are called nodes and not vertices, is a terminology, and a finite set of directed lines, we use only directed lines here, which are called as arcs and that connect these pair of nodes. So, for example, here A is a root. Now, we normally use tree terminologies. So, A is a root, B and I are here internal nodes, and then the rest of the C, D, G, H, I, L, G, H, I, all of them are leaf nodes, internal nodes or branch nodes or leaf nodes. So, you have a root, you have internal node, root is the first node, the head node or so to be called, which is the root of the tree, then you have internal nodes and then you have leaves. That is the basic terminology of trees. So, use trees to represent relationships. Trees are hierarchical in nature. What is the meaning of hierarchy? You have a first, under that some nodes, under that some nodes. So, it is hierarchical in nature. Parent child relationship is often described between the nodes in the tree. So, the root is a parent of an internal node and generalized to ancestor and descendant. If you say ancestor, it is grandparent and grandparent, that is easier to understand, you see. Descendant is child, grandchild and so on. The lines between the nodes are called as edges, and a subtree is a tree in any node of the tree together with all its descendants. So, if you have, that is called a subtree, we will see with figures later on as we go. Ancestors of a node are parent, grandparent, great grandparent, grandparent and so on. Descendants of a node are a grandchild, grandchild and so on. Depth of a node is the number of ancestors that are there, and the height of a node is the maximum depth of a node, and degree of a node is the number of its children. Okay. And degree of a tree is the maximum number of all its nodes. So, let us look at this on a degree of all its nodes. So, let us look at the terminology here. Here root without the root is the parent, root a node without a parent, and that is A here. Siblings are nodes which share the same parent. For example, E and F are siblings because they share the same parent B. So, that is siblings. Siblings is brothers and sisters in a normal term. Internal node is a node which has at least one child. So, it should have at least. So, what are the internal nodes in this particular example? A is an internal node, B is an internal node, C is an internal node, and F is an internal node. So, all the ones that are colored blue are internal nodes. It should have at least one child, okay, A, B, C, F. External nodes are leaves without any children. So, all the green nodes here are extra leaves. For example, E, I, J, K, G, H and D, all of them are leaves or external node. A subtree is a tree consisting of node and all its descendants. For example, here C, G and H is a subtree, that is a subtree. Okay. So, C, G and H is a, so each node of a tree may have a subtree. So, you have this two subtrees. Subtree of all nodes includes its children and all descendants, which as we have already seen. Now, let us look at the kinds of trees. You have a general tree, it is a set T of one or more nodes such that T is partitioned into disjoint subsets. A single node R, the root, sets that are general trees are all subtrees of R. So, n-ary tree, set of nodes that are either empty or are partitioned into n disjoint subsets. So, single node and n possibly empty sets that are n-ary subtrees of R. Binary tree is a special case where we have either empty partition into disjoint subsets, single node R the root, and two possibly empty sets that are binary trees called the left and right subtrees of R. So, R is the root node. So, generally you have n-ary or binary, n-ary is general. Okay. So, the tree's representation, it is a very common and important. The tree terminology, nodes have one parent only always. The nodes children are leaf nodes will have no children, roof node will have no parent, we have already seen this. Data structures that store trees are important. Execution or processing that can be expressed as a tree is also an important aspect. Example, method calls as a program run, all these can be represented. Searching a maze of puzzle can also be represented as a tree, that is execution or processing. Now, what are the importance of trees? Trees are very important for cognition and computation. Okay. In computer science, language processing, where in language processing is used for parse trees, knowledge representation for modeling the real world, family trees, taxonomy, kingdom, species and so on. So, this is a very important applications of trees. So, that is why it is said that it is used in language processing and knowledge representation, where modeling the real world where it comes into cognition. Now, let us take an example of a tree which is a file system. So, here you have a real time example. So, you have the C colon, the drive, under that you have 3 folders, under that C216 you have 3 folders, lab 1, lab 2, lab 3, lab 1 you have 2 files, and under lab 3 you have 1 file and so on. So, this is an example, and then you have my mail where you have school and one thing. So, in the C drive you have stored it like this. It is a typical representation of the directory file system in a now, another example is XML and HTML documents. Now, let us take an HTML document you have there. You have a HTML document which consists of a head and a body. So, you have H1 my page, then you have the pages, and then you have the body of the HTML file and HTML. How is this a tree and what are the leaves? How is this a tree and what are the leaves? That is important. So, how do you represent that? You represent it in different ways. So, you will start with the head, and under the head you will have and so on. So, that the recursive definition is very natural way of representing trees. So, a recursive data structure, now let us, before we go further with trees, let us discuss what is a recursive data structure, very important concept that we will be using throughout trees and further on. So, a data structure that contains a pointer or reference to an instance or itself is called a recursive data structure. So, you have a tree node, and the tree node T left right, then tree node T parent, and then you have tree node. So, this is the definition of the tree node. The tree node itself consists of 2 subtrees which are again tree nodes, left and right and parent, then the parent of the node. So, recursion is a natural way to express many algorithms, and for recursive data structures, recursive algorithms is a natural choice. So, recursive algorithm, to use a recursive algorithm, recursive data structure seems to be a natural choice. And now let us go to the next slide, which is tree ADT. So, we use positions or to abstract nodes. Okay. So, we will just use that. So, generic methods are integer. Now, what are the methods associated with tree? Remember, we are using tree, I mean we are using the abstract data type to method of talking about trees, and in any abstract data type you have to associate what is that data structure along with the operation. So, now we are discussing the general methods that has to be associated with the tree ADT. So, you have an integer, I mean you have a size, what is the size of the tree, is the tree empty, which is always a Boolean operation, and then you have what are the elements of the tree. This is important, what are the elements, I will tell you why this is important later on. Then you can give positions of the tree, okay. I will tell you what this position means, this is specific to tree, and then you have accessor methods, that is how you want to find elements in the tree. You can find the root, it will give you the position of the root, it can give you the parent of a particular node P, it can give you the children of a particular node P. So, all these are accessor methods, you find the root of the tree, you find the parent of a node, you find the children of a node. Then you have query methods, is internal, given a node P, is it internal, okay. Given a node P, is it external. Remember, internal nodes are nodes that have children and external nodes are nodes that do not have children. So, it is trying to find out internal nodes and external nodes or leaves. You can try to find out whether P is a root of a tree. So, those are all query methods. Then you have update methods. What are the update methods you have? Swap elements, 2 elements of a tree you want to swap, replace an element in the tree with another element. You can have additional update which may be defined by the data structure that is particularly implementing the ADT. So, basically in a tree ADT you have generic methods where you find the size, the number of nodes, other words, whether the tree is empty or not, what are the elements of the tree, and what is the positions that the tree is occupying. I will come to those positions a little later, because it is implementation dependent. Then you have accessor methods, you want to find the root of the tree, you want to find the parent of a particular node, you want to find the children of a particular node. Then query methods is we want to find whether a node is internal node or an external node or a root. And then update methods where you want to swap nodes or replace elements. Here we have not done, the update does not talk about insertion into a tree or deletion from a tree, those things we have not spoken about, we will talk about a little later. Now, let us look at how do you represent a tree node. So, a tree node basically intuitively how do you represent? Remember, we are talking about general nodes. So, you can have a data and you have links to all its children. Okay. So, this is a typical intuitive list representation. So, let us assume the tree can also be represented as a list like this. So, the root comes first, followed by a list of links to its subtrees and so on. So, the number of link fields needed is in such a representation is not known, because it is a general tree, you do not know how many children a tree can have beforehand, I mean sorry, a node can have beforehand. So, it is very difficult to represent this. Okay. So, what do? Every tree node will be an object, and it will have useful information like what is its data, and children will be pointers to its children. So, you can see here the first node, the parent has 3 children, and we are assuming 3 children, and so each of the children, if you see in the node here, you will see that it has no children, and the next one has 2 children, and the next one has only 1 child. Okay. So, this is another representation where a node is represented as an element, parent node and a sequence of its child nodes. So, let us assume we have B, A, D, F, C and E as the nodes, where B is a parent, A, D are its children, and A and F are leaf nodes, and D has 2 children C and E. So, you start with B, and the data is given there, that is the element. The parent node is null because B does not have any parent, and then you have a link to its children. It has 3 children, you can see there the pointers to its children. And then if you look at that node, that is pointing to 3 nodes A, D and F, the children of B. Now, A is the element you see here, and then the A's parent points to B because that is its parent, and it does not have any children, so it is null. Then you take D, the node D, and then it has a parent to the node B, and then it has a link to the pointers of its children C and E, and F has null. And here if you see, the children are null, the parent points to D, here the point E also the parent points to D. So, this is another general tree representation. What you have here is the children will be there will be a pointer to the children. So, now one way to implement a general tree is to use a node structure uses the left child right sibling representation. This is a very interesting representation. This is one way of representing the general tree. Okay. So, specifically given a node n, its left you will have only 2 pointers there. The first pointer will point to the leftmost child, and the right pointer will point to the linked list of all other siblings of that leftmost child, or the right you can't say right, or the other children. So, its right pointer points to a linked list of nodes that are siblings of n, where n is a given node. So, let us look at that. So, suppose you have a left child right sibling, I am sorry, it points to the siblings. So, suppose you replace the left child sibling representation A, you put the left child of A, and then the node's left link will point to all its siblings. So, here you have B pointing to its next sibling and C pointing to its sibling. Then you have B, its child and its siblings. Here you have H and sibling, and here you have J, K and that sibling. So, if you see here, data points to the left child, A does not have only left child, it does not have siblings, okay, it is a root node. B has child E, I mean leftmost child is E, and B's siblings are C and D. E has leftmost child J, and E siblings are F and J, and so on. So, this is called the left child right sibling representation. So, here you have a representation, and we are assuming it is an array representation. So, you have the parents index. So, the R is a label here, this is a parent pointer implementation. So, you have node index is 0, R is the label and it does not have any parent. Then 1 is occupied. Now, this is the position. Now, if you look here 0, I mean 0, 1, 2, 3, 4, 5, up to that you have 5, 6. So, it occupies all the 6. The only information that is available there is the parent information. So, here you have R point having a parents index is null, 1 has A has parents index 0, B has parent index 0, C has parent index 1, because it is occupying its point, it has to point to A and A is occupying 1, and D also has 1, E also has 1, F has 2 because B is occupying position 2. Similarly, if you see the other tree, another tree W, X, Y, Z, all of them are pointing to its parent. W will have null, X, Y, Z will point to the position of W, which is 7. So, it is not that it depends on where in the array the parent is located. So, this is the parent pointer representation. Now, you have in tree traversals, you have in each of these traversals in order, pre order and post order, you have 2 main methods associated with it. So, it is a recursive definition. Traverse in 2 methods as we told you, traverse in order the left subtree, visit the root, and traverse in order the right subtree, please remember, not right child. So, pre-order, you visit the node first, root first, then go to the pre-order of the children and then the pre-order of the children. Post order, you traverse the post order of the children, visit the root. So, this is the tree traversals. Now, let us take an example of in-order traversal. A traversal visits the nodes of a tree in a systematic manner. In in-order traversal, the leftmost subtree is visited, then the node is visited, then all the other subtrees are visited before its descendants. So, if you take the algorithm in-order leftmost subtree visit V, for each subtree other than the leftmost subtree W of V, you do an in-order. So, it is a recursive definition. We will see how this is done. So, first I will visit, this is the in-order traversal. So, first I will visit the leftmost node, then I will visit the root, then I will visit the right node. Now, this subtree is over, that is the leftmost subtree, okay, that is the first step. Now, I have to visit the node, so I will visit the node. Now, I have to visit each subtree. So, first I will visit this subtree, but that has to be done in order. So, I will visit the left subtree, root, and then the right subtrees. Now, I finished the subtree that is rooted at methods, 2 methods. Now, leftmost subtree is visited, rightmost subtree is visited, each of them is visited in using the same algorithm, and then finally, I will visit the next subtree, but that has only one node. So, it is visited. This is the order in which the nodes will be visited or traversed. It will be traversal, means you are visiting a node only once or listing the node only once. So, this is the order in which it will be visited. So, to repeat again, first you have in order leftmost subtree. So, you have to go to the leftmost subtree. In that leftmost subtree, which is this subtree, starting with motivation, there you have to visit the leftmost subtree. So, that is how you come to empty life or whatever first. Now, we will take the same tree and use it for pre-order traversal. So, a traversal visits the node of a tree in a systematic manner, that is what is traversal. In a pre-order traversal, a node is visited before its descendants. Application is a print a structured document, we will come to that later. So, this is the algorithm visit V. For each child of W, do the pre-order. So, here what we do, you have to visit first, then you go to the leftmost child first. Normally, it is done left to right manner. So, leftmost child pre-order, then pre-order that does not have children. So, you visit it, go to the right, visit it. Now, you go and now you have visited the one child is over, go to the next child, visit the root, all its subtrees in or all its children in order, then you have finished this subtree, go to the next child and do. So, this is the order. If you look at the previous and this, the orders are vastly different. We will go into this detail and make you understand this when we are doing binary tree traversal, but just to tell you that traversal is not only for binary, but also for general trees. I have just taken this example. Now, you go to post order. Post order is you have to first visit the children before you visit the parent. So, here in post order traversal, a node is visited after its descendants. So, in this we have taken another example here. So, if you take this example, you will visit this first, then both the children, then its parents. So, you finish this subtree. Now, you have to finish all the subtrees of the root. So, you go here, the children, all the children, its root, then you visit this, and finally, you will go to the root node. So, this is post order traversal. Now, what is the problem with general trees and its solutions? That is what we are going to discuss. The problems are the number of references for each node must be equal to the maximum that will be used in the tree. So, you do not know how many references you will need, that is how many children you will have, you do not know. So, you assume that you have 10 children, all the nodes have to have that. So, most of the algorithms for searching, traversing, adding, deleting nodes become much more complex, in that they must now cope with situation where there are just not 2 possibilities as in binary tree, but any number of possibilities, multiple possibilities are possible for each and every node. So, that is the problem with general trees. So, the solution is normally even if you have a general tree representation, because the application demands a general tree representation, you do not use general trees, you convert these general trees to binary trees. So, in this module we are also going to see how to convert general trees to binary trees. The algorithm that is used for binary tree processing can then be used, that is why the optimized algorithm that is used for binary tree processing can then be used without with only very minor modifications, because you have converted this general tree to a binary tree. And most of the algorithms that we talk about are to do with binary trees. So, now what I am trying to tell you here is what the application demands a general tree, do not worry, design initial design you do with general tree, then convert it into a binary tree and then do all the algorithms. That is how most of the applications are handled. Now, so for that we need to know how to convert a general tree to a binary tree. So, there is a systematic procedure for this. What is the systematic procedure? Use the node root of the general tree as the root of the binary tree, that is the first step. So, you have a general tree with any number of children, use the root of the tree as the root of the binary tree. Then you determine the first child of the root. Okay. This will be the leftmost node in the general tree in the next level. So, every time you take the first node, we actually leftmost, in binary tree we have the terms left child and right child, here we do not have first child or leftmost child, that is you are assuming the children are from left to right. So, you take that leftmost child, insert this node into the binary tree, the child reference of the parent node refers to that node. So, now you have that. Now, continue finding the first child of each parent and insert it below the parent node. So, what you have done up to this point is you have found the leftmost left child, not leftmost, left child of the binary tree round order. Now, when no more first children exist, move back to the parent of the last node entered and repeat this above process to the next child. So, that is what is done. Complete the tree for all nodes. For completing the tree, the sibling next to the first child is made its right child and its sibling becomes the right child and so on. To understand this, we will do a simulation now. So, this is a general tree. The first node has 3 children and I think C has 3 children. We have just taken a simple case so that we can demonstrate this. Now, remember what is the first step? First step is the root node of the general tree is the root node of the binary tree. Okay. So, root of the general tree, I am calling this as a general tree. Now, the first child of A becomes the left child of, remember in binary tree we have only left child and right child. So, first child of A becomes the the first child of the A in the general tree becomes the first child of A in the binary tree also. Now, you take the first child of B, that is K, that becomes the left child of B. So, there it is over because K does not have any children. Now, what you do? You take the sibling of B, you try to take the sibling of K, K does not have any sibling, take the sibling of B and the sibling of B becomes the right child of B, the first sibling. So, that is the second step. Now, you take the sibling of C, that becomes the right child of C. Okay. And now, you take the first child of C, we have not handled C yet, take the first child of C, that becomes the left child of C. Now, the sibling of H becomes the right child of H and the sibling of I becomes the right child of I. Now, you have not still finished the tree, you have finished up to D. Now, you take the first child, that becomes the first child of D and the sibling of F E becomes the right child of E and the first child of F becomes the left of H. So, this is the final binary tree that is equivalent to the general tree. What have we done here? We kept going to the first child, we will call it first child in the general tree and the binary tree we will call it as left child. Okay. So, first child of A becomes the left child of A, the first child of B becomes the first child of B or left child of B. Now, B's right sibling, the sibling of B becomes the right child. So, always sibling is the right child, first child is the left child, you keep doing that and so the question comes, if I have B, C, D all are siblings, B's right is C, C's right child is D and so on. Okay. Child will be left and sibling will be right, that is the basic concept of converting a general tree to binary tree, we have shown you that. Now, what is the summary of this module we talked about? We did not talk about binary trees, we are going to talk about binary trees in detail in the next 2 modules. So, here we are going to talk about only general, we spoke only about general trees, we explained what is the concept of trees in terms of the terminology that was used. Then we discussed general trees, what is with some examples, we used basically we used a file system to explain these examples. Then we described some representation of general trees, one is an array representation, one was a parent node representation, one was left child right sibling representation. Then we explained the different tree traversals in terms of general trees, we did not go too much into detail, but explained that it was a recursive algorithm and that was very conveniently described using this algorithm, this particular traversals, and then we outlined the conversion of general trees to binary trees. So, in the next module we will be talking about binary trees in detail, which is much more used and has a lot of algorithms associated with.